In this video, I continue with numerical solutions of ODEs. The examples in this video are driven harmonic oscillations, which have the form given in line 6. So on the left-hand side of the equation, we have the damped harmonic oscillation. On the right-hand side, we have a driving force, which is denoted by F of t. As before, in the last video, we have to convert this second-order equation to a system of two first-order equations by the usual substitution, and we get a similar function handle as before, but now the function handle has one additional argument, which is the driving force. The first entry in this vector of functions is the same as before in the last video. The second entry is similar to before. What we have now we have to add the driving force on the right-hand side of the equation in line 9. So this is all the information for the solver. We define a time span. We define the coefficients A, B, and C such that it's weakly damped, which means that there is resonance. This system cannot be characterized by some well-known physical concepts. First, we have the natural frequency, Eigenkreisfrequenz in German. We have the decay constant, Abklingkonstante. We have the characteristic frequency, Kennpreisfrequenz, and we have the resonance frequency, Resonanzfrequenz. So let's display these values. We set some initial conditions for the oscillation, for the driven oscillation. We set the amplitude of the driving force to A equals 1, and we consider now the solutions for 3 different driving frequencies and 3 different driving forces. The first one is just a sinus. The second one is an alternating function, and the third one is a saw blade function. So first we have a loop over the different types of driving force, and for each driving force we have a loop over the 3 driving frequencies. So we choose one of the driving frequencies in line 42. We specify the driving frequency by substituting the chosen driving frequency in the handle dr force. Force is now a handle that depends only on t. And then we call the solver OD23. Again, we have to convert this handle, which depends on Ty, ABC, and the driving force, to a handle which depends only on T and Y. This handle is anonymous. The arguments are the same as before. The handle that specifies the first order equations, the time span, and the initial values. There are no options in this case. So we solve, and now we plot the solution. So in the upper plot we see the solution in blue, the driving force, the sinus driving force in red dotted, and it's hard to read. Okay, so the driving frequency is 0.5. In this case, the solution follows slightly behind the driving force. We have to distinguish between two parts of the solution, the initial part and the persistent part. The initial part is the weakly damped system that decays, and the persistent part is just enforced by the driver. So now we have a different driving frequency. In this case, the driving frequency is just the resonance frequency, and this means that we have the largest amplitude. You see that the amplitude is now much larger than before. It's in the order of 4, whereas it was slightly larger than 1 with a small driving frequency. You can also see that the solution is shifted by about pi over 2 with respect to the driving force. Now let's pass to a large frequency of the driving force, much larger than the resonance frequency. In this case, we see that the amplitude gets rather small and that it is shifted with respect to the driving force by pi, 180 degrees. So when the driving force goes up, the solution goes down. Now we can repeat this with different shapes of the driving force. We now have an alternating driving force which alternates between +1 and -1. At small driving frequency, the solution is certainly not a sinus function. At the resonance frequency, the amplitude is almost 5. So it's much larger than before. It's again shifted by pi over 2, and with a large driving frequency, we again get smaller amplitudes and a shift of pi, half a period. Okay, the third driving force is a saw blade function. And the picture is very much similar as before. Non-sinus shape with small driving frequency, sinus shape, and a shift of pi over 2 at the resonance frequency with larger amplitude, and small amplitude and a shift of pi with a high driving frequency.